Hello, everybody, and welcome to the last day of PChem. You were waiting for this one for a while. So, today we're going to be looking at metal complexes as you get ready for inorg next year. So, we're going to be specifically looking at the orbitals of a metal complex. So, one of the really useful things in order to examine how orbitals undergo electronic spectroscopy is to first understand a lot about the energy of their individual orbitals. And as always, we can use symmetry to really help simplify these systems. So we're going to start by examining a relatively idealized version of a set of metal orbitals. We're going to work with an idealized octahedral complex, such as titanium hexachloride. It is worth noting that these same basic principles hold for a lot of other octahedral complexes, even in the presence of differing ligands, though there can be slight modifications on the basic idea. So if I have an idealized octahedral complex, this means my system should be placed in OH symmetry. So I have an OH point group, and then I can go ahead and assign irreducible representations to my various metal orbitals. Now, in octahedral symmetry, you can go ahead and look up your table. You can find that we'll split them into two different categories. So our dz squared and our x squared minus y squared orbitals are going to be placed in a doubly degenerate EG irreducible representation. And my triply degenerate dxy, xz, and yz will all be placed in the T2G irreducible representation. And one of the reasons why they're going to, and since both of these systems have different irreducible representations, we shouldn't be too surprised that they can possess different energies because, well, they're going to be in slightly different environments when exposed to these metal, to the surrounding metal ligands. And this is going to be one of the biggest reasons why why they should be placed in different degeneracies. These three orbitals will all experience the same net effect, and these two orbitals, again, pointed along the major axis, either being the z-axis or the xy axis, are going to directly point at these ligands. And because they point straight at these ligands, they're going to experience much greater electrostatic repulsion. Because in general, ligands tend to be electronic rich, and I'm going to end up generating a lot of electron-electron interaction, which can increase the electrostatic repulsion, decreasing the stability of these orbitals. So in general, what we tend to find is that my EG orbitals will be unstable and relatively high in energy, and my T2G orbitals are going to be relatively lower in energy as they'll be stabilized. And we can essentially give the difference in energy of these two sets of orbitals by delta O, or the octahedral ligand field splitting parameter. It is worth noting, though, since I've got three T2G orbitals, they're going to have to go down in energy less than the EG orbitals go up. So 3/5 of the difference will be the destabilization of my doubly degenerate orbitals, and 2/5 of it will be the stabilization of my triply degenerate orbitals, as these orbitals will tend to have a much more maximized interaction with the ligand. Now, one of the important things to note is that what I have is ligand interactions are helping stabilize these slightly off-center interactions with the triply degenerate orbitals, while destabilizing due to direct overlap with the EG orbitals. So what we're going to tend to see is we're going to have a greater uh, ligand field splitting parameter for ligands that have a greater interaction energy. So these tend to be ligands with a lot of electron density and high metal interaction. So the more interaction with the ligand the metal has with the ligand, the greater I should expect this field splitting parameter to be. Now, here comes a question. How can I try and go about determining this field splitting parameter? Well, it turns out that I can see some extent of metal of D to D orbital transitions. And these will have characteristic wavelengths. So it is worth noting, this, while not observable for all molecules, you can often observe the wavelength for this D to D transition, which will be directly related to the octahedral field splitting parameter. So this is a nice direct way to measure the metal ligand interaction energies. Now, one of the other very useful things about these field splitting parameters is this energy gap often ends up occurring somewhere in or near the visible range. And this is actually really useful. And it's one of the reasons why so many metal compounds tend to be colored. It's due to these D to D transitions, which is actually quite cool. And gives us a lot of information about the bonding character of so many different metal atoms. However, one of the things that is worth noting, both of these d orbitals do possess Girard symmetry. So this means that while this absorption does occur in the visible spectra, it's often not as bright as it could be because it's often highly suppressed, as these transitions are Laporte forbidden, which, as a reminder, means that I can't have a Girard to Girard excitation, because it turns out my photon's Ungerad, and it only wants to hang out with Ungerad. Go figure. But we do see mild extents of this interaction, which can be quite useful. However, it is worth noting, not all metals are octahedral. Turns out some of them are tetrahedral. We can repeat the same similar process for tetrahedral metallic complexes. So the first thing I'm going to do is go into my tetrahedral point group, and I'm going to identify the irreducible representations for my two sets of d orbitals. This time, it turns out that my orbitals are still split up the same way. dz squared and x squared minus y squared are part of an E point group. And this time, the xy, xz, and yz orbitals are part of the T2 point group. It is worth noting, this time we don't have T2g or EG, because guess what? Tetrahedral complexes don't have inversion symmetry. Well, that makes that at least a little bit easier. But it is also worth noting that we do kind of have an inversion of who's lower in energy here. And the reason why is actually largely the same reason we had for octahedral complexes. For octahedral complexes, it was my z squared and x squared minus y squared that pointed straight towards the ligands, increasing electrostatic overlap. Now, if we go ahead and look at the axes, it turns out that these orbitals are going to kind of split in between the axes. It's hard to see in this particular representation, but it is actually true. Whereas the xy, xz, and yz point straight towards the ligands, destabilizing them. However, again, we do see that the e orbitals are more stabilized than the triply degenerate orbitals, again, because there's less of them, so they have to carry extra weight. However, at this time, it works out in their favor. And again, this is going to generate its own type of energy field splitting parameter, this time given as delta T to indicate we have a tetrahedral splitting parameter. And this is actually going to be independent of the octahedral splitting parameter. However, it is worth noting that they are both going to depend upon the extent of interaction of the ligands with the metal center. However, it is worth noting that in this case, despite not having Girard symmetry, if you go ahead and look up your tables, character tables, and you try and see if it's possible to excite from E to T2, you're going to find it still doesn't work. So this D to D transition is still technically symmetry forbidden. However, that doesn't mean we don't see some small extent of D to D transitions, albeit with a much lower intensity. Now, one of the things I want to quickly take a moment is trying to compare these two sets of orbitals. And when we're trying to look at the favorability of an octahedral versus a tetrahedral complex, this is actually going to be driven by a fair number of phenomena. First of all, it's going to be driven by nuclear charge, because this is going to help determine how close these orbitals are to the center, their extent of interactions with each other, and their extent of interactions with the ligand, which is also going to be driven by the strength of the metal ligand interaction, essentially how widely split the system is. It is worth noting, field splitting parameters tend to be much larger for octahedral complexes than for tetrahedral, because they're more pointed directly towards the metals instead of essentially off center. And this does indeed make a difference when trying to compare the orbital energies. But one of the largest driving forces of figuring out which species is going to be favored is simply the number of d electrons. So if I only have a handful of d electrons, the fact that the tetrahedral complex is tetrahedral energies are more highly stabilized as a fraction of the field splitting parameter can often favor the formation of tetrahedral complexes for low valence metals, such as titanium. Whereas as I increase the number of electrons to get to the point of iron, where I have 6 electrons, we tend to favor octahedral complexes. You also may notice early in the semester, I told you that having 6 electrons was actually fairly favored for metallic complexes. And this octahedral binding coordination is one of the reasons why, that 6 electrons can often be more highly favored than a simple 5. So we often tend to find stabilizations of 4, 6s, and then if we have to, things like 7s and 8s, as they're going to maximize filling of these less favorable excited state d orbitals when you're dealing with species like nickel and copper. However, if I have a metal that is relatively electron poor, so anything that's essentially d6 or lower, we still have to worry about the tendency of these d to d transitions, as we'll have the excitation into those low-lying empty orbitals because my d orbitals have split. Now, one of the things I do want to emphasize is, well, uniformly, these d to d transitions are technically symmetry forbidden. One of the reasons why they are weakly allowed is because molecules are more complicated than we think. And tetrahedral and octahedral complexes are both vulnerable to vibrations. And most importantly here, we have those asymmetric vibrations. So these are going to be things like out-of-plane vibrations, which allow the molecular orbitals to slowly deviate from original symmetry. And these slight deviations from symmetry can help allow the orbitals to essentially deviate just enough from symmetry, so we might see some excitation at certain points along the vibrational trajectory. And this is the reason why these transitions can occur, but they're always going to occur at low intensities because they're only going to occur while the molecule is vibrating and at only certain points during the vibration. So in general, all these d orbital excitations tend to occur with fairly low probability. However, there are certain mechanisms that do allow orbital excitations to occur with a much higher probability. But to do that, I have to try and identify some symmetry allowed transitions. So if they're not coming from inside the metal d orbitals, I have to look outside. And this is going to happen as I start including my ligand orbitals. So I want you to at least be aware of a couple types of charge transfer. The first of which is ligand to metal charge transfer. So you may imagine I go ahead and I mix, I have my metal coordinate to the ligand. And while I may have no actual coordination, exchange of electrons in between the d orbitals and the sigma orbitals of the metal complex of the ligand complex, what I may end up doing is seeing some sort of modification of the orbital levels. So my sigma or my ligand orbital should be stabilized, whereas I should see my metal complex tend to separate into its bound orbital levels. Often this is going to happen by splitting into an octahedral complex. So I will increase the energy of my uh, z squared and x squared minus y squared orbitals. Now, it turns out that as long as my ligands are in the right geometry, it should be possible to excite into either a low-lying empty, most likely EG orbital, but occasionally an empty T2G, depending upon configuration. And so these results can often occur still within visible spectra, usually a little higher in energy than usually higher in energy than a D to D transition, but with a much higher intensity, which is a nice offset when trying to make vibrant colors. However, it is worth noting that I am essentially transferring an electron from the ligand into the metal. So I'm essentially going to be reducing the metal center. However, this excited state may end up decaying to regenerate the product, but it isn't too surprising. A lot of these types of dye may be vulnerable to essentially what's called light bleaching. So if I expose it to enough radiation, I will have transferred enough electrons to the metal that eventually it will be fully reduced and the coordination complex may fall apart. And that's something to worry about in terms of dye stability. However, if it's possible to to promote electrons from the ligand to the metal, it should theoretically be possible to do the reverse. So this is known as metal to ligand charge transfer, and it most commonly occurs if I've got a metal complex. It's going to go ahead and split into either an octahedral, most likely an octahedral, but occasionally a tetrahedral complex. And then I have lots of empty pi networks. So generally, a lot of electrons on my metal, few electrons on my ligands. Specifically, we like thinking about things with good sets of pi orbitals. Molecules like CO2, cyano groups, acetonitrile, anything with a good empty pi system is perfect. So I can then excite directly from the octahedral complex into these low-lying pi star orbitals. So this will be higher in energy than a traditional D to D transition, but again, it often occurs with a much higher intensity as long as I share symmetry in between these same groups. However, it is worth noting that this is going to have the opposite problem of a ligand to metal transfer, as I'm slowly going to oxidize my metal center, often at the tendency of reducing my ligands. One of the reasons why this can be specifically potent is because if I'm promoting enough electrons into the pi star system, this can occasionally promote degradation of our ligand system. So with this kind of last summary of how we can use our knowledge of orbitals and electron excitations and apply it to inorganic systems, hopefully I've given you a good idea of how we can make use of quantum mechanics in the future and prepared you at least a little bit for a wonderful semester in Inorg. Been great having you. Take care and stay safe.